A small device mounted on the wall may seem insignificant, but when billions of them operate at once, they become one of the largest electrical loads on the planet, consuming more than 2 trillion kilowatt-hours of electricity every year. Every second, roughly 10 more air conditioners are sold worldwide, nearly 9,000 new units in the time it takes you to watch this video. To keep pace with that staggering demand, massive steel coils are stamped into durable outer shells, thin sheets of aluminum are sliced into thousands of heat-dissipating fins, and copper tubing is bent and sealed to form the circulatory system that carries heat. Finally, the compressor, fans, circuit boards, and refrigerant are brought together, awakening a machine capable of quietly pulling heat from a room and releasing it outside. The invention that helps billions of people endure extreme heat was not originally created to keep people cool. In 1902, at a printing plant in Brooklyn, humidity caused the paper to repeatedly expand and contract, throwing the color layers out of alignment and ruining entire print runs. The young engineer named Willis Carrier developed a system capable of controlling both temperature and humidity, laying the foundation for modern air conditioning. The cool air the workers felt at the time was merely an unintended side effect. From a solution designed for a handful of printing presses, air conditioning gradually made its way into factories, movie theaters, offices, hospitals, and billions of homes. It not only transformed how people live through the summer, but also enabled industries that require tightly controlled environments, such as electronics, pharmaceuticals, and data centers, to operate with precision. Few could have imagined that the global cooling revolution would begin simply because several layers of colored ink refused to stay properly aligned on a sheet of paper. Before an air conditioner can be assembled, the factory must prepare dozens of material and component groups according to the exact configuration of each model. Cold-rolled steel coils, weighing anywhere from several tons to more than 11 US tons, are transported to the factory by train or specialized truck. Inside the raw material warehouse, overhead cranes, equipped with automatic lifting clamps, pick up each coil from the receiving area and move it either to its designated storage position or directly onto a feeding stand. Every coil is inspected for material grade, thickness, and surface quality before being transferred to the stamping line. Meanwhile, copper tubing arrives wound into large coils to save space and minimize deformation during transportation. Once inside the workshop, it is uncoiled, straightened, and checked for dimensional accuracy before being cut into individual lengths. Because copper conducts heat many times more efficiently than ordinary steel, it will eventually form the network that carries refrigerant throughout the system. Aluminum foil, electrical wiring, circuit boards, and electronic components are also sorted into separate batches. From this point forward, these previously disconnected materials are ready to enter their own specialized production lines. From the raw material warehouse, steel coils weighing several tons are lifted by an overhead crane and positioned precisely onto an uncoiling stand. As the spindle begins to rotate, a steel strip stretching hundreds of feet gradually unwinds and passes through a series of rollers, where it is flattened before entering the automated stamping press. Here, every time the dies close, tens or even hundreds of tons of force simultaneously trim the edges, punch mounting holes, form ventilation openings, and stamp reinforcing ribs into the metal. After only a few press cycles, the flat steel sheet has become a base pan, side panel, compressor mounting bracket, or part of the outdoor unit's casing. Robots then transfer the components to a press brake, where the tooling bends the metal along pre-programmed angles, completing each three-dimensional structure with accuracy measured in fractions of an inch. Industrial cameras and sensors continuously measure dimensions, verify hole positions, and detect distortions nearly invisible to the human eye. This seemingly simple layer of steel is actually the structural skeleton that must support a compressor spinning at thousands of revolutions per minute while enduring rain, sunlight, and changing temperatures for years. After being formed, the metal components are degreased, thoroughly washed, and surface treated to remove dust, oil, and other contaminants that could cause the coating to peel away. They are then suspended from an overhead conveyor and carried one by one into the powder coating booth. Inside, spray guns apply an electrical charge to millions of ultrafine powder particles. The oppositely charged metal draws the powder evenly across flat surfaces, bent edges, and narrow corners that liquid paint may struggle to reach. The coated components then pass through a curing oven heated to approximately 350 to 400 degrees Fahrenheit. At this temperature, the powder melts, bonds to the metal, and forms a hard, uniform protective film. Once cooled, workers measure the coating thickness, test its adhesion, and inspect the surface for uneven coverage. This coating does far more than add color. It becomes a protective suit of armor, helping the outdoor unit withstand humidity, rain, and corrosion for years. The plastic pellets are first fed into a dryer to remove moisture that could create air bubbles or weaken the finished part. They then enter a heated barrel, where a rotating screw pushes the material forward until it melts completely. The molten plastic is injected into a mold under high pressure, flowing into every narrow channel to form the front panel, air louvers, and other components of the indoor unit's casing. Once the plastic cools and hardens, the mold opens, and a robot quickly removes the finished part before the next cycle begins. Ultra-thin aluminum fins are first fed continuously into a high-speed stamping press. In a single stroke, the die punches openings for the copper tubes, while forming raised ridges that strengthen each fin and increase its contact area with the air. The finished fins are then stacked into a dense block, with nearly uniform spacing that allows airflow to pass through without excessive resistance. On a neighboring production line, copper tubing is uncoiled and pulled through a series of rollers to straighten it. A cutting machine divides the tubing into programmed lengths before a bending machine forms each section into a U, resembling an oversized hairpin. These repeated bends allow the refrigerant to travel a much longer route within a compact space, giving it more time to absorb or release heat. Robots or workers then thread each copper tube through hundreds of aluminum fins. An expanding rod is pushed through the tubing, increasing its diameter by only a tiny amount, just enough to press the copper firmly against the aluminum. The tube ends are finally brazed together to create a sealed refrigerant circuit. From this point on, copper and aluminum no longer work separately. The tubing carries refrigerant like blood vessels, while the fins rapidly transfer heat to or from the passing airflow. Once the copper tubes have been threaded through the aluminum fins and mechanically expanded into place, workers begin sealing the refrigerant circuit. Each tube end is cleaned, carefully aligned, and heated with a torch. When the copper reaches the proper temperature, the brazing alloy melts and is drawn into the joint by capillary action, forming a strong, airtight bond as it cools. During heating, nitrogen may be fed slowly through the tubing. This protective flow helps prevent oxide from forming inside, tiny flakes that could later break loose, travel through the system, and create blockages. But a clean, polished joint is not always a leak-free one. The completed coil is pressurized with test gas at a specified pressure. Sensors monitor for any pressure drop, while leak detectors scan every connection. Any suspicious joint is marked, repaired, and tested again. Because a gap, almost invisible today, could allow refrigerant to escape, gradually robbing the air conditioner of its cooling power after several summers. The indoor unit's cross-flow fan and the outdoor unit's axial fan are molded, fitted with their motors, and then placed on dynamic balancing machines. On a neighboring production line, the control system begins to take shape. Automated machines cut electrical wires to programmed lengths, strip away the insulation, crimp the terminals, and bundle them into model-specific wiring harnesses. The main circuit board, inverter module, temperature sensors, and protective components are then powered up for signal testing. This is the brain of the air conditioner. Every second it operates, the control circuit continuously monitors the room temperature, compares it with the selected setting, and adjusts the speeds of both the compressor and the fans. On the assembly line, the empty plastic housing begins to fill out like a body gradually taking shape. The first components installed are the condensate drain pan, insulation, and drain hose. Together, they create a sealed pathway that collects moisture condensing on the indoor coil and carries it outside instead of allowing water to build up and drip down the wall. Next, lifting equipment lowers the evaporator coil into locating grooves molded into the housing. Workers align the copper tube connections before securing the entire assembly with screws or locking clips. Even a small installation error could disturb the airflow or create vibration during operation. The cylindrical crossflow fan is positioned behind or beneath the heat exchanger and connected to its motor. As it rotates, hundreds of small blades running along the blower draw room air through the chilled aluminum fins and distribute the cooled airflow evenly across the full length of the outlet. At the next station, the circuit board, temperature sensors, remote control signal receiver, and louver motor are installed in sequence. Wiring harnesses are routed through dedicated retaining channels, keeping them safely away from the spinning fan and the condensate area. Finally, workers fit the front panel, air filters, and directional louvers. They manually rotate the blower, activate the louvers, and listen for any scraping or unusual noise. Only when the airflow moves smoothly, evenly, and in the correct direction is the indoor unit cleared to leave the station. On the outdoor unit assembly line, the protective coated base pan is positioned precisely on a fixture. Workers install rubber vibration isolators before a lifting device lowers the compressor, the heart of the system, into place and secures it with bolts. These seemingly simple rubber mounts prevent compressor vibrations from traveling into the metal cabinet, helping reduce noise throughout operation. The compressor is typically manufactured on a specialized production line because its internal moving parts must fit together within extremely tight tolerances. But why is the component responsible for cooling placed outside the room? Because the compressor does not directly produce cold air. Instead, it compresses and drives the refrigerant through the system, carrying heat from indoors to the outside. Next, the condenser coil, fan motor, fan blade, partition panel, and electrical enclosure are installed around the compressor. Depending on the design, workers may also add a reversing valve, expansion device, accumulator, and pressure and temperature sensors. The copper tubing is bent, carefully aligned, and brazed shut, connecting the components into one continuous closed loop. Retaining clamps are added to prevent the tubes from striking the cabinet during vibration. Finally, wires from the compressor, fan, and sensors are connected to the control board. At this point, the outdoor unit is ready to receive heat from the room and release it into the outside air. At this station, the refrigerant circuit is first pressurized with test gas. An automated detector scans every valve, connection, and brazed joint, searching for leaks that are nearly invisible. Once the system passes inspection, a vacuum pump begins removing the air and moisture trapped inside. The vacuum is held steady for a set period because even a small amount of moisture can react with the oil, cause corrosion, or freeze at the expansion point. Finally, the charging machine reads the model code and dispenses the exact programmed weight of refrigerant. The service tube is then sealed and inspected one last time. Many production lines are also transitioning to refrigerants with a lower impact on the climate. At the final testing station, the indoor and outdoor units are connected as a complete system. Once the compressor starts, sensors measure temperature, airflow, pressure, power consumption, and noise. Industrial cameras and microphones detect fan contact or unusual vibrations. Each unit is also checked for current leakage, insulation, and grounding. Every result is compared against the limits set for that model, and only air conditioners that pass the full inspection are cleared for packaging. After passing every inspection, each air conditioner is given its own fingerprint. A label displaying the model, serial number, electrical rating, and refrigerant type is printed, attached to the unit, and scanned, linking the product to its complete manufacturing and testing history. The indoor and outdoor units then enter separate packaging lines. Each assembly is wrapped in a protective bag, secured between molded cushioning blocks, and lowered into a cardboard box. These supports hold the equipment firmly in place, absorb impacts, and prevent the copper tubing from being damaged during a journey that may stretch for thousands of miles. Finally, the tracking code is scanned once more, and the boxes are stacked on pallets and transferred to the warehouse. The two halves of the system now temporarily part ways, only to be connected again at the installation site. From coils of steel, copper tubing, and thousands of individual components, an air conditioner gradually takes shape through a series of precisely controlled stages. The cabinet is formed, the heat exchangers are bent and assembled, while the compressor, fans, sensors, and control board are integrated into a closed-loop system. But the process is only complete when every brazed joint passes leak testing. The refrigerant circuit is evacuated, and the exact amount of refrigerant is charged. The indoor and outdoor units must then prove their cooling performance, safety, and quiet operation before being packaged. Behind a seemingly simple stream of cool air lies a carefully coordinated system of advanced materials, precision engineering, thermodynamics, and rigorous testing. The two halves now leave the factory separately, waiting to be reunited and begin their first cooling cycle in a room thousands of miles away. If you want to continue exploring massive manufacturing processes like this, subscribe to Factron Process. See you on the next journey.